Let's learn about two ideas related to sufficiency and sufficient statistics: ancillarity and completeness. First, let's learn what an ancillary statistic is. If you're watching this, you've probably learned something about sufficient statistics, which contain all the information about the parameter theta. If not, watch my videos on sufficient statistics and minimal sufficient statistics first. You can find them in this playlist or in the description. An ancillary statistic, on the other hand, is the opposite of a sufficient statistic. It contains no information about theta. It's independent of theta. So here's an example. Let x1 through xn be a sample from a uniform distribution between theta and theta plus 1. Okay, so this is a uniform distribution that is 1 wide. Okay, its width is 1. And let's define the range to be the max minus the min. Well, how big do we expect the range to be? Well, the maximum is probably going to be close to theta plus 1, and the minimum is going to be close to theta. So the range should be about 1. It will be a little bit less than 1, and it will be closer to 1 if we have a bigger sample size. But it doesn't depend on theta, right? It does depend on the sample size, but it does not depend on our parameter theta. It is ancillary, meaning it is independent of theta. And this is related to the idea of location families and having measures of spread be ancillary in a location family. Right, so in any location family where the various distributions are just shifted versions of each other, the range will be an ancillary statistic. So we saw that with the uniform distribution. And a normal distribution is a location family too. Okay, if we're only letting the mean vary, then all the different normal distributions are exactly the same, just shifted over. So the range is ancillary. Its distribution does not depend on the mean. Right, the range does depend on what sigma, the standard deviation, is. The range will be bigger when sigma is bigger. And the range will depend on n. The range will be bigger when n is big because we're going to see more weird observations. But the range does not depend on mu. Similarly, we have scale families. Okay, so in scale families, the various distributions are just scaled versions of each other, which could be viewed sort of like a change of units, right? So suppose that we have our data x, which follows an exponential distribution with rate lambda, and let that be the waiting time in hours for an event that occurs at a rate of lambda per hour. Well, then if y is the same waiting time in minutes, y has an exponential distribution with rate lambda over 60. And since the y is directly related to x using this formula, when we take a ratio of times, whether we measure that time in hours or measure it in minutes, the ratio is the same. Okay, so the ratios of various values are identical regardless of the units, regardless of the scale, meaning regardless of what our parameter lambda is, whether it's lambda or lambda over 60. So various types of ratios are ancillary to the parameter. They do not depend on the parameter. So in scale families, many types of ratios are ancillary. So ancillary was sort of the easy part. Now let's learn about completeness. So let's say we have a family of PDFs. Okay, so this is our sufficient statistic T, and the distribution of our statistic, of course, is going to depend on our parameter theta. So that's what this theta means, that the distribution of T depends on theta. And we call the family of probability distributions complete if the expected value of a function g of t is 0 for all theta, right? So if this is true, then that implies that g of t, that function of our statistic, is equal to 0, right? So how can this expected value be 0? Well, that just means the function is always 0 with probability 1, right? So, maybe there's a set of probability 0 where it is not equal to 0, but for the most part, the function has to be equal to 0 with probability 1 for all theta. Now, I know this is a mouthful, but we'll see this in action a lot. And for short, we're often just going to call T of x a complete statistic. We're not going to call it a family or a complete family. Often we're just going to call T a complete statistic. So let's see some examples to kind of wrap our head around this definition. And just to note, this part about for all theta is very important. This has to be true for all theta out of all possible theta in our parameter space, big theta. Right? So that's the set of all possible parameters that we can have. And completeness depends on the parameter space. And we're going to see an example of this, where if we don't pay attention to that part, it makes our statistic not complete. So let's look at a statistic that is not complete. So here's just our definition of what a complete statistic is. And let's let our data be a random sample of size n from a normal distribution with mean mu and standard deviation or variance 1. Well, the statistic x1, x2, right, the first two observations, is not complete. And why is that? Well, let's define a function, g of t, as x1 minus x2. And what is the expected value of g of t? Well, g of t is just x1 minus x2. So the expected value of x1 minus x2 is 0, regardless of what mu is. Okay, so the expected value of this is 0 for all mu. Based on our definition, if that's true, if this is 0 for all values of our parameter, then if this is complete, if t is complete, that implies that the probability that g of t is equal to 0 is 1. That g of t is always equal to 0. But g of t is not always equal to 0, right? x1 minus x2 very rarely is going to be 0. So this part is true, but this is not true. So this is not a complete statistic. So let's look at another example that is not complete. So let's have, again, a random sample, an IID sample from this uniform distribution between theta and theta plus 1. And let's look at the range, right? We said this is ancillary. So the expected value of this statistic, the max minus the min, is ancillary. So its expected value is some number c that's probably close to 1, but it does not depend on theta because it's ancillary. So let's let g of t be t, right, the range, minus its expected value, c. So what is e of g of t? Well, that's just equal to e of t minus c. And we can prove that that is equal to 0. So the expected value of a function of t is 0. But the probability that that is 0 is not 1, right? The range is not always equal to its expected value, right? So sometimes this thing is not going to be 0, right? Most often it's not going to be 0. So this is another example of something that is not complete because we can find a function whose expected value is 0 that is not always 0. So how do we find a statistic that is complete? And they are really hard to find in a lot of cases. So here's two examples of proving a statistic is complete, and we'll see how hard it can be. So let's let our statistic t follow a binomial distribution with parameters n and p. And suppose we have a function g such that its expected value is equal to 0. Okay, so its expected value is 0. So 0 is the expected value. And what is an expected value? Well, an expected value is the function times its probability and the sum of that. So this function is equal, right? So this expected value here is equal to 0. Now, if t is complete, that means that this function must be equal to 0, right? This g of t must be equal to 0. And is that true? Well, it's not at all obvious. These numbers here are all positive. So do these numbers have to be 0, or could we make a function that maybe sometimes is negative, sometimes is positive, and will always be 0, regardless of what p is? And this is actually impossible unless g of t is 0. Now, this argument is not very interesting and has nothing to do with statistics, so I'm not going to talk about it very much. But basically, because of the form of this polynomial, there's just no way we could find a function except 0 that makes this always equal to 0. And thus, that function has to be 0 with probability 1 for every single p. So t is a complete statistic because if this is 0, this expected value, then g of t does have to be 0. And again, this is not at all obvious. One more example with a uniform distribution. Let's say we have a sample of data from a uniform distribution on 0 to theta now. And you might be familiar with the fact that the maximum is a sufficient statistic for theta. And the maximum, this is the PDF of the maximum. Okay, so let's suppose we had a function where the expected value of g of t, right, a function g of the maximum was equal to 0. And since the expected value is 0, its derivative with respect to theta is also 0. All right, so the derivative of this thing with respect to theta would also be 0. And again, this is sort of an out there argument, which just really proves that it's very hard to prove completeness in general. So 0 would be equal to the derivative of this expected value, which we could compute is 1 over theta times n times g of theta. And this has to do with the fundamental theorem of calculus and some complicated integration. Okay, so that allowed, so this complicated integration that I'm not showing led us to this. And can this thing be 0? Well, theta is not 0, right? So this thing's not 0. N is not 0, our sample size. So that means g of theta has to be 0, right? So g of theta must be 0 for all theta. Okay, so this is a complete statistic. And again, this is not all obvious. And my only point in these examples really is to show you that proving a statistic is complete is sometimes pretty dang hard and involves some mathematical trickery that is very particular to the individual problem. However, if our distribution belongs to an exponential family, finding a complete statistic is quite easy, right? So we have all these distributions that belong to what we call exponential families, where the PDF can be expressed in this form. And most distributions that we're familiar with belong to this. Not the uniform distribution, but the normal distribution, exponential, binomial, gamma, and many, many more. Okay, so this is how we write exponential families. And when we write things like this, t is actually the sufficient statistic. Okay, and if this parameter space, right, so if the set of all possible parameters contains an open set or an interval, basically, then t is also complete, right? So t is sufficient in an exponential family, right? We always have a sufficient statistic in exponential families. And it's often also complete if we can prove the parameter space contains an open set, right? So an open set is like an interval from A to B, right? This is an open interval. It's an open set. Now, if we have 2 dimensions, it is like a circle, and we might call it an open ball. So let's look at an example of this. Suppose we have our data, which is normally distributed with mean mu and a known standard deviation 1. So the sufficient statistic for a normal distribution is just the sum or the mean, right? The sum or the mean are both sufficient. So we have a one-dimensional sufficient statistic. It's just one number, the sum. And mu can take any value, right? Mu can be any number. So this contains an open set, an interval in R, right? A huge interval. The whole real line is an open set. So because our parameter space contains an open set, this statistic is not only sufficient, but it's complete. Now, suppose we have our data, which is normally distributed with unknown mean and unknown variance. Well, in that case, we'd have to use the factorization theorem to find a 2-dimensional sufficient statistic, which would be the sum and the sum of the squared data. We might also see it other ways, right? We might see the mean and the standard deviation, but this is equivalent to that. So now that we have a 2-dimensional sufficient statistic, we want to know if our parameter space contains an open set in R2. Well, our parameter space is all real numbers for mu and all positive numbers for sigma squared. Okay, well, what values can this pair take? It can really take any number. If we imagined R2, this set can really take any value in the upper 2 quadrants of a plane, right? So that's a huge amount of space that contains a lot of open sets. Okay, so there is a complete statistic there. Now, here's a counterexample. Sometimes we have curved exponential families, okay? And let's suppose we have a data set xi where we have a normal distribution, where we have a mean mu, and we have a standard deviation that's also unknown, a variance that's unknown. And the variance, though, is exactly equal to the square of the mean. Okay, so it's exactly equal to the square of the mean. So we don't have that freedom that mu and sigma are separate. They're related to each other, and this is called a curved exponential family. So the sufficient statistic, again, is going to be our sum of the xi and our sum of the xi squared. And so we want to know, does the parameter space contain an open set in R2? Well, when we look at the pair mu squared, and if we drew this, this is no longer a whole space of the plane, right? It's not a whole, the whole upper two quadrants of the plane. This set of points defines a parabola, right? And a parabola is just a line that does not contain a whole ball, an open set in R2. So because there's no open set, there's no complete statistic. This is sufficient, but not complete. Another counterexample is when we have weird parameter spaces. Okay, so let's let our xi be normal, mu with a known standard deviation, a known variance 1. And we said that if mu could be any number in the real numbers, that the sum would be complete, right? It's sufficient and it would also be complete. But what if our parameter space doesn't contain an open set? What if mu, we know, can only be an integer, right? Maybe positive integers or negative integers or 0. But if that's true, there is no open set, right? This is just discrete numbers on a number line. There is no interval that is possible, right? There's lots of gaps. And so we can't use this theorem that this contains an open set to prove that it is complete. I'm not very good at trigonometry, so I'm not going to prove this for you here. But I think we could find some function related to cosine to find an unbiased estimator of 0, right? To find a function g of t, which is this cosine, that is equal to 0, where the expected value is equal to 0, but it's not always equal to 0, right? So obviously cosine is not always equal to 0, but because at the integer values here, this would take value 1, I think we could find a function of this that would be 0 everywhere. So that might not be obvious at all, but this doesn't contain an open set, so this would not be complete. So we've seen a lot of examples here, but what does completeness even mean? Right? So let t be a statistic that is sufficient but not complete, and let f of t be some unbiased estimator of theta. Right? So we want to estimate theta, and we want to use our sufficient statistic to estimate theta, right? So we have a function of our sufficient statistic that estimates theta in an unbiased way. Well, since t is not complete, there is a function, g of t, that isn't always 0, but where the expected value is 0. And what that means is we could define a new estimator, h of t, and let's let it just be f of t plus g of t. Well, what is the expected value of this new estimator? Well, by properties of expectation, it's just equal to theta. It's still unbiased because g of t is an unbiased estimator of 0, so it doesn't change the unbiased estimator. So h of t is a different unbiased estimator of theta, and it might have a lower variance, right? Maybe h of t is a better estimator than f of t. So when our statistic is not complete, what happens is maybe we don't know that our estimator f of t is the best, because I could just add this extra info to it and get another unbiased estimator that perhaps has a lower variance. So let's see an example of that. Again, let's let xi be normal in this curved exponential family, right, where we have a mean theta and a variance theta squared. So our mean and our standard deviation, our sample mean, our sample standard deviation is sufficient for our theta, but it's not complete. Okay, so if we define a function of our sufficient statistic as n over n plus 1 x bar minus s squared, the expected value of this function is 0. So that's not at all obvious, but it is 0, just believe me. And of course, this function is not always equal to 0, right? If we take some number times the mean minus the sample standard deviation, that number is definitely not always going to be 0. So the expected value is 0, but it's not always 0, and thus it is not complete. So x bar, we know, is an unbiased estimator of theta, and x bar plus g is also an unbiased estimator of theta because it has expected value 0. So when we add it, it doesn't change the unbiasedness. And which has a lower variance? Well, who knows? It's not exactly obvious which one is going to have a lower variance. It makes sense that perhaps when we calculate the standard deviation too, which involves the xi squareds, because the standard deviation, the variance is related to theta in this way, that maybe incorporating that information would give us an estimator with a lower variance. So now we have a lot of unbiased estimators we have to consider, and we don't exactly know which one has a lower variance. And this is related to this idea of the Lehmann-Scheffé theorem, which states that if t is a complete sufficient statistic for theta, and the expected value of g of t is equal to some function of theta, right, which all that means is that we can use a function of our sufficient statistic to estimate a function of theta, which might be theta itself, right? So t is estimating theta, or g of t is estimating a function of theta, and g of t is an unbiased estimator of h of theta. Well, if t is complete and sufficient, then g of t is the uniformly minimum variance unbiased estimator of h of theta. Okay, so what this means is when we have a complete sufficient statistic t, and we take some function of it, that will have an expected value that depends on theta. And we don't even have to check what the variance of this is and prove that it's the best. It's always going to be the best. Okay, g of t is always going to be the best minimum variance unbiased estimator of h of theta. Okay? If t is a complete sufficient statistic, g of t is the UMVUE of its expected value. So estimators based on complete sufficient statistics are the best unbiased estimators, always. A little more on the relationship between sufficiency and completeness. If a minimal sufficient statistic exists, then any complete statistic will be minimal sufficient. Okay, so complete statistics are not necessarily minimal sufficient, but if there is a minimal sufficient statistic, then the complete statistic will be the minimal sufficient statistic. Okay, so complete statistics are in a lot of ways very similar to minimal sufficient statistics in the sense that they don't contain extra information, unnecessary information. So in a sense, a complete statistic is the opposite of an ancillary statistic. And this idea is formalized by Basu's theorem. Basu's theorem states that if t is a complete and minimal sufficient statistic, then t of x is independent of every ancillary statistic. So t being complete and minimal sufficient means that it contains no extraneous information about our parameter, and so much so that if we have an ancillary statistic that is independent of the parameter, t is independent of that ancillary statistic. And knowing that two things like this are independent makes a lot of calculations much easier because of the nice properties of independence. Looking at the family of normal distributions with unknown mean and some fixed known sigma, x bar, our sample mean, is complete and sufficient for mu. And the sample variance is an ancillary statistic. So that means that x bar and the sample variance are independent. And this is a nice property of normal distributions, that the mean and the sample variance are independent. And this is only true in normal distributions. And we use similar facts about independence when computing things like t-statistics, which depend on the independence between x bar and s. Thanks for watching. Please like and subscribe to learn more statistics.